it turns out there's something nice about this spec, because this spec does get minus signs into the picture by definition. And I kind of intimated that, like, if you don't get minus signs into the picture, like, nothing good is ever going to happen. Because, like, for something good to happen in quantum, like, you need this interference to do something cool where, like, positive and negatives get canceled out. So this is, like, a cool spec to have because, like, baked into the spec is that, like, you're going to get some positives and negatives, and then maybe they'll cancel out in a cool way when you do the Hadamard. But it's a little bit unnatural, and it's a little bit of a trick in the sense that it, like, heavily relies on M being 1. Like, yeah, okay, if there's one output bit, like, there's two possibilities, so you're like, okay, cool, there's two signs here. I can use plus or minus 1. But like, what if there's two output bits? Since there's, like, 4 possibilities, you're like, I don't see any logical, like, extension of this. That's true. So when M is bigger than 1, we're going to have, like, a different scheme, like a different spec. And that different spec you can also use when M equals 1. But this is like a very useful spec in the M equals 1 case because it already gets these negative signs that we kind of know we need baked in. So again, this is just the spec. I didn't tell you if you have, like, code for computing palindromes, regular classical code, or regular classical code for computing primality. I didn't tell you how to get quantum code that does this spec. But we will see that in the next lecture. And it's not too hard. It's, like, literally a mechanical procedure that converts the classical code into the quantum code that does this spec. Like, you could write a program that took the classical code as a text file and outputted the quantum code as a text file. That's easy. But we'll save that for later. Okay, so let me address what I hope your question was, which is, this is a bit funky. What are we going to do in general? So I will tell you what we're going to do in general. But in fact, before I tell you what we do in general, I'll tell you what we do in general when M is 1 again. So this is like an alternate system, an alternate spec you could sort of desire in the special case where M is 1. Special case like 2 prime, still like M equals 1, but it's a different system. And this system is like, I'm going to try to make this. If f of b1 through bn, then toggle c. And I hope you know exactly what I mean by this. It's a bit different. So like here, the spec only involved n qubits, and it didn't change the fact that there are n qubits. Here, this spec is like, if you want to do this quantum version of palindromes or whatever, you need to actually have an extra qubit called c. And then the spec is like this. And this is kind of nice, because this is classical reversible. This is classical, obviously. I mean, it does what you think it does, okay? That's the definition. I won't write it, but like it does what you think it does. This is classical and reversible. Why is it reversible? Because it's its own undo. Because we've seen this basically before, right? If you do this instruction twice in a row, like it exactly changes nothing. Because like it doesn't matter like if f on the first, the input qubits is true or false, you maybe toggle c. But if you do it twice in a row, like you either toggle it 0 times or 2 times, so nothing happens. So therefore, this is a classical reversible operation, and therefore it's unitary, therefore it can in principle be done. So this is like a valid possible thing to want a quantum code to do. So that's good. So that's it. So then, like in principle, we kind of know this ought to be programmable. Because I promised you that every unitary transformation really is programmable. And same story, like next time we will see how to program this. We will see how to actually get quantum code that only uses, toggles and if-then, blah, blah, blah toggles. That accomplishes this for any f. And it's like a mechanical procedure that like takes in the source code for CCode and that computes f, and it spits out the quantum source code that does this. It's quite simple. We'll see it next time. And just want to notice we've encountered this before, actually. Like we already have this in many cases, like when f, is like a 2-bit thing, f of b1, b2 is b1 and b2. Then it's like, oh, this is literally the if, b1 and b2 then toggle c thing. And like when it's like b1 or b2. This one, like I didn't give you as a pseudocode instruction, but then like on homework 1, question 1, I was like, program this for yourself. So now we have this instruction. And I also asked you on the code to do this one, like f, or on the homework to do this one. F of b1 is like not b1. Now this one's actually reversible, so we could have used special case 1 here. But you also saw that you can make if not b1, then toggle c. And we also have this for like f b1 equals b1. That's a simple function, but if you plug it into this recipe, like that corresponds to the instruction, like, if b1, then toggle c. Which is sort of like already one of our basic pseudocode instructions. In fact, we also have this for like this function, the function that takes no inputs at all, n is 0, and outputs 1. What pseudocode instruction does this correspond to when you put it into this recipe? Yeah?
Just toggle C.
Just toggle C, yeah. Right? Like if, it wasn't palindromes or primality, but like I was like, please tell me about this recipe when f is the Boolean function that takes 0 inputs and always outputs the single qubit 1, then you'd be like, okay, like the quantum spec is going to be if, well, just 1, then toggle C, which is like logically equivalent to just always toggle C. And you're like, hey, I know how to do that one. There's a single instruction, toggle C, I'm done. In our pseudocode, like the quantum code, there's like a single instruction for this one. This one, it took you maybe 3 instructions or something. So what I want to tell you is that like literally for any Boolean function, you can make, in principle, quantum code that does this. Moreover, if you have classical code that does f, you can easily transform it into quantum code that does if f, then toggle C. And by the way, why is that? Or like, I claim you should pretty much believe me on that. Because you all know, I'm sure, this like, canonical computer science fact that like every Boolean function can be made up from ands and ors and nots. And you're like, well, if every function can be made up from ands and ors and nots, and I kind of already have like if b1 and b2 then toggle, and I have if or then toggle, and if I have if not then toggle, then probably I can just like put them together to like make this. Yes. Yeah, we'll do that next time. Yeah. Yeah, the question is about like, what if you need additional bits to keep track of stuff? Actually, maybe there's like 2 things you could be asking here. Like, one, what if the classical code has like additional internal bits it uses to like program f? You're like, okay, I got to program f. First thing I'm going to do is like declare a few variables. Those are like new bits on the side, and then I don't know, do like some loop or something. Yeah. Well, excellent point. When I slightly lied to you. When we next time, see the quantum code that like implements this, it will also need to like allocate some new qubits on the side to help it do that. You probably even got the sense of this maybe on homework 1. You're like, am I allowed to like allocate some more qubits to help me? And I was like, no, you cannot. Well, for the general case, yes, I'm going to have to allow it. So this I didn't want to like talk about this until next time, but I'll mention it to you right now. This will actually, we won't actually get this. We'll get an instruction that's like if f then toggle c and new qubits like junk 1 to junk 100 or something. So like the actual quantum code, it will accomplish this, but it will also, on the side, generate a bunch of other qubits. But it'll like leave those qubits as 0. It'll like clean up after itself. And we're just going to accept that. We're just going to accept that the fact that all our quantum implementations, they do the thing they want, and they put some qubits that are 0 somewhere. And we'll be like, that's fine. But indeed, like, you cannot in general do this without like allocating some more like workspace and like additional variables to help you do the computation. Okay. So I've told you all the special cases. Now I will tell you the general case. The general case. Which is like, okay, if m is not 1, f is not reversible, like it's just any old Boolean function, what is going to be the definition of the spec? And it's not too hard. In fact, we're rarely actually going to need this general case, but, you know, we'll do it. General case, m is maybe greater than 1, but we'll say even m greater than or equal to 1. So the spec will be, or QCode will be, I'll write it like this. Toggle f of b1, so like the input bits, bn, onto c1 through cm. Okay, so the spec will be like, I'm going to need n plus m qubits. And like whatever, I'm going to treat the first n as the input. And then, you know, it's going to be like, I will kind of compute f's value, which is an m-bit string. And then I will like XOR it onto these m output bits. So here, like maybe you could also call it XOR. Okay. So like XOR this answer onto these bits. So why is the spec designed this way? Well, this is a classical type instruction in the sense that, you know, if all the inputs are just a basic state, the output will be a basic state. It just converts bits to bits. It's also reversible. No matter what f is, this is a reversible instruction for basically the same reason. Like, well, it doesn't matter if this what the output string is here. If you do this twice in a row, it's not only is it reversible, it's its own reverse. It's its own undo. If you do this twice in a row, it cancels out. Because whatever this output string is, you toggle it onto C, the C bits, but this doesn't change. The B's don't change. So if you do this instruction a second time, B's are still the same. F of B1 through Bn is the same m-bit string. So you effectively toggle this one m-bit string onto these bits twice. And we know like toggling twice or XORing twice like cancels out. So I hope I just convinced you this is a classical reversible operation. And therefore, as we know, therefore, like it's unitary, it's quantum eligible, we're happy. Like this can be, in principle, done by a quantum computer. Moreover, 90% of the time, when we're going to use this, you might be like, this spec, it's kind of weird. Like 90% of the time when we use this, we're going to have C1 through Cm all set to 0. And what happens in the special case where C1 through Cm are all set to 0? Well, like you toggle like the correct answer onto all these zeros. It's just like setting these bits to the correct answer. So this really kind of does like implement f, you know, like if you plug in the first n bits to be the input string you care about, and you plug in the remaining m bits to be, I should say qubits, to be all zeros, and then you do this instruction, then you just get the answer in the last m qubits, and the first n qubits actually don't change. The input also sticks around. So like cool, like I kind of got the input-output pair. In general, you can do this instruction when these are not all zeros, and then you kind of you like bit mask the answer of this computation onto these bits. And 10% of the time, we will actually take advantage of that fact. We'll be like, oh, I'm glad it does that, because I'm going to use that. But 90% of the time, we'll just be like, these will be zeros anyway. So let me make some comments about this. First of all, again, well, okay. First of all, if m happens to be 1, then this just becomes like toggle the answer onto C1, which is just like another way of saying these words. Okay, this is another way to say like if the answer is 1, then toggle C, otherwise don't toggle C. So if m equals 1, this is the same, just in different words, as the special case. So it's like a natural generalization of the m equals 1 case. And just like in this special case, I'm here to tell you that in the next lecture, we will see the following, that if you have classical code that computes a function f, there's like a simple mechanical procedure which transforms it into quantum code that does this, toggle f of b1 onto, et cetera, onto c's. So that's cool. So let me just summarize what we've seen. We saw 3 cases, or 4 cases maybe. Kind of saw f happens to be reversible. And in that case, we'll generally take the spec to just be, the quantum spec to just be like literally do f. Then we saw like f, outputs 1 bit. And we're using this like if then minus thing. That's one possible choice. Then we also saw that like you could have f that has m equals 1, but we're doing the like if then toggle thing on this left board. And these are like 2 valid choices, and you could decide to do either in your life. And then finally we have the general case, like f has m greater than 1, and then there's like only one option. It's like this toggle f onto some c's. And what I'm going to show you next time is the following. Next time we'll see how to do this. We'll see how, given classical code for computing a function with 1 output bit, we can easily transform into quantum code that does the if f then toggle. That will be the main step. And then we'll see that's like gives us the power for everything. We'll see like once you have this, it's easy to get that. Once you have this, it's easy to get that. And once you have this, it's easy to get that. And so the main work will be to just like figure this out, and then I'll show you, oh, once you have this, you can get this spec, you can get this spec, you can get this spec. And that's how we use quantum to compute classical functions.